7-2, inverse functions and relations. A relation is a set of ordered pairs. An inverse relation are two relations where the x and the y values in the ordered pairs are switched. For example, if one relation has the point AB, then the inverse relation has the point BA. Here's a good example for you. In set A, we've got 1, 2, 3, 4, 5, 6. In set B, we've got 2, 1, 4, 3, 6, 5, where the x and the y values are swapped around. Thus, A and B are inverses. So here's example 1. Find the inverse of the relation. Well, in an inverse, by definition, all I need to do here is switch the x and y values. So the inverse relation will be 4, 2, 1, -3, and 8, 2. There's kind of a cool thing that happens when you graph inverses. They end up being mirror images across the line y equals x, and I'll show you that coming up. So an inverse function, usually we write in function notation, f of x and f inverse of x. That's how you read it with this little power of -1. We read it as f inverse of x. So in function notation here, f of a equals b, if and only if f inverse of b equals a. Notice again that the x and the y values are swapped. The domain and range values are swapped. a, b is an f, b, a is an f inverse. So how do you find an inverse function? Well, we're going to replace f of x with y to begin. Then you swap x and y, because in an inverse function, x and y are switched. Then you can solve the resulting equation for y, and then finally you can write your answer in function notation as f inverse of x. Here's how it works. So I'm going to start by rewriting it as y equals instead of f of x equals, just because we don't want to deal with function notation. So y equals x plus 6 over 2. That's step 1. Now step 2, you're going to switch x and y. Basically, their places in the equation. So you're going to write x equals y plus 6 over 2. Swap them. Now we've got the inverse function here. X and y are switched. We're going to solve this one for y. So I'm going to multiply by 2 on each side. 2x equals y plus 6. Subtract 6 on each side. And we have 2x minus 6 equals y. Here's my inverse function. Now that I've got it solved for y, the last thing to do is to write it in function notation. So f inverse of x is 2x minus 6. Okay, so let me go through those steps one more time with you. Here's the original function. We switch x and y, switch their places in the equation, resolve it for y, get y by itself, and you've got the inverse function. Finally, write it in function notation. F inverse of x is 2x minus 6. These two functions here are inverses. Okay, so what does that mean? Well, here I'm going to show you the graph. So we're going to graph the function and its inverse. Here's the original function. Let me draw the graph quick. Positive 5 is our y-intercept. 1/2 is your slope, so you can count up 1 over 2 from that positive 5. That's your rise over run, or I can go down and to the left 2. Okay, so here's the first line. There we go. This one was y equals 1/2 x plus 5. Okay, let's find the inverse function now and graph the inverse function, and I'll show you what they look like. So to find the inverse function, I'm going to switch the placement of x and y in the equation. So I'm going to write x equals 1/2 y plus 5. X equals 1/2 y plus 5. Now, if we resolve this equation for y, get y by itself, we'll have our inverse function. So I'm going to subtract 5 on each side. X minus 5 equals 1/2 y. Then I'm going to multiply each side by 2 to get the y by itself. On the left here, I'm multiplying the entire side by 2, so I need to put it in parentheses and use the distributive property. So we get y equals 2x minus 10. We're going to distribute this 2 through. 2x minus 10. There we go. Oh, I have an extra 1 in here. Minus 10. Okay, so here's our inverse function. The y-intercept is negative 10. Hold on here, let me try to move my graph. Y-intercept is negative 10. I'm just going to kind of go down negative 10, right about there. And then our slope is up 2 over 1. Up 2 over 1. Up 2 over 1. Here we go. Okay. Good enough. Here's our line. Okay, so the red is the original, the blue is the inverse function. F inverse equals 2x minus 10. Keep putting an extra one in there. There we go. 2x minus 10. Now the cool thing about inverses is that they're a mirror image. They're a mirror image across this line, center line, y equals x. Let me plot the mirror line real quick here. I'll just do it dotted. Here's the mirror. And now the function and its inverse are mirror images, or they're symmetrical about this line y equals x. On the line y equals x, x and y are always the same, 0, 0, 1, 1, 2, 2, 3, 3. And so that graph and its inverse are exactly the same. But if you notice here, a function and its inverse have x and y values switched. Like look at this point. In the original it was 0, 5. In the inverse it's 5, 0. And so you've got a mirror image here across this center line. The point 2, 6 is 6, 2 in the inverse. And so it's a mirror image straight across. Draw a dashed line. There's the mirror image. 2, 6, 6, 2. So when you graph a function in this inverse, they're always going to be mirror images of each other because each x and y value is swapped or switched around in the inverse function. Kind of cool. Okay, finally, how can you tell if two functions are inverses? Well, we're going to use the composition of functions. So two functions are inverses if and only if both of their compositions are the identity function f of x equals x, or y equals x. You can think of it that way. So what you need to do to check if they're inverses is check to see if f of g of x gives you 1x, and then you also have to check the other way, that g of f of x also gives you 1x. If you can prove both of these, then you know you've got inverse functions. If one of them is not true, then they're not inverses. So example 4, determine whether the two functions are inverse functions. We need to check and see that f of g of x equals x and g of f of x equals x. So let's start with f of g of x. So I'm plugging the g of x function into x in the f function. So I'm taking f of 1/5 x minus 2. So that means this is my input into the f function right here. So I'm going to write 5 times 1/5 x minus 2 plus 10. I've replaced x with the g of x function. 5 times 1/5 is 1x minus 5 times 2 is 10. Then we've got that plus 10, and so we do get x. That's good. The first way checks out. Now I need to check g of f of x. So I'm going to use the g function this time, and I'm going to plug in f of x, 5x plus 10. So 5x plus 10 will go into x. So we've got 1/5 times, in parentheses, 5x plus 10 minus 2. That's our g of x function with f plugged in. Okay, so we're going to distribute again where we have these parentheses. 1/5 times 5 is 1x. 1/5 times 10 is positive 2, so we get x plus 2 minus 2, and we get x. Check. Okay, so we've just proved that these two are inverses. We have inverse functions. Let me show you one more of those. Determine whether the two functions are inverse functions. You can't always tell just by looking. It might look like we've got inverse functions here, but it helps to check. Okay, so let's compose f of g of x. So I'm going to start with the f function here, and I'm going to plug in g of x, 1/3 x plus 4. Okay, so following the rule for f here, we're going to put in 1/3 x plus 4 in place of x. So we've got a 3 out in front. Then in parentheses, now I'm going to input 1/3 x plus 4. Then outside I've got the minus 3. Well, let's distribute here. 3 times 1/3 is 1, so we get 1x plus 3 times 4 is 12, and then I've got a minus 3. Am I going to end up with 1x here? Well, no, I'm not. I get x plus 9. We already know that these are not inverses because I did not get x. You don't even have to check g of f of x. You don't even have to compose them in the other direction. We already know that these are not inverses because I didn't get x. Okay. All right, this is the end of the lesson. I didn't include any check for understanding problems. We will definitely do that in class. Make sure that you watch this video a couple times if you need some review.